Good evening. My name is Subodh Nimka, and I am Strategic Marketing Manager based in San Jose for clinical and toxicology. So in this talk, I'm going to spend more time on applications and not so much on how the hardware works. As the title suggests, it is about application of ultra-high resolution LCMS, mainly in the area of forensic toxicology screening. So what I want to do in this presentation is basically do a little bit of introduction of this new mass spectrometer that we launched late last year, which is Exactive. This is based on Orbitrap technology that Julian just talked about. Then I will show you an example, just one example of how this technology can be used to monitor certain large number of drugs in serum sample and how easy it is. This technology is really about ease of use. For a simple lab which does not have huge expertise to do screening, that's where the Exactive comes into picture and offers benefits. Then for this particular application, what was the sample preparation? What LCMS method was used? How the resolution and mass accuracy impacts your results and how beneficial it is. How does it translate to final identification of drugs in serum? Show some data about LOD and LOQ and how that relates to resolution and concentration of drugs in the sample. And then basically conclude. So this is a schematic of Exactive, which is based on the Orbitrap technology. What you have here, this is where the ion source is, and this takes the heated electrospray source. The ions are formed here, and then this is the ion packet that is going through. So ions formed here, they're transmitted through the lens. It goes through all these lenses, comes to the C-trap. Now you've got the ions in the C-trap. This instrument also has a collision cell if you wanted to do MSMS. But for majority of the screening applications, just ultra-high resolution and accurate mass is enough. So if you are not using the HCD cell, then the ions are basically transmitted from the C-trap into Orbitrap, and where the scanning and the Orbitrap happens, and you get the high resolution exact mass. If you had the HCD cell on your instrument, then the ions that are here, that are sent into the collision cell, fragmented, they're sent back to the C-trap after fragmentation, and then pulsed into the Orbitrap. That's really how the Exactive mass spectrometer works. Now just quickly, what does that do for us? It offers 100,000 resolution at a scan speed of 1 second. And you can obviously run it at 10,000 resolution, which is somewhere like a QTOF resolution. The mass accuracy of sub-ppm, very high sensitivity, dynamic range of about 10,000, very good quantitation device. and I'll show some data. As you can see, you can scan it as fast as 10 scans per second, and mass range from 50 to 4,000. That means it's great for both small molecules as well as for large intact proteins. It does allow you to do polarity switching. So for example, in small molecule applications where there are some basic drugs, there are acidic drugs, and in forensic screening, you really don't know what you're monitoring or what you're expecting. So you need to switch continuously between positive and negative ion. And the Exactive technology lets you switch between positive and negative ion. So what does this really offer you? What's the tremendous power it brings? So this is an example. I think most of you who have run LC-MS must be quite familiar with the problems with the pallets or phthalates. There is constant background which is at around 270 ANU, which comes from peak tubing and other parts of your HPLC, and that constantly raises the background. Now, in this case, this is an example of 100 parts per billion of an hormone sample, which is 500 picograms on column. And the analyte here, or the drug here, is estradiol. Now, estradiol and phthalate have identical mass. Isobaric at a resolution of 10,000. Cannot distinguish between the two. So if you inject 100 parts per billion of estradiol and run it at a resolution of 10,000, this is what you see. Perfect noisy baseline. There is nothing that really stands out as a peak. The same injection, same thing, now you run it at 100,000 resolution, that's what you get. So here now this is a comparison of 10,000 and 100,000. And as you can see, now if you, in the same LC-MS run, if you extract this mass with less than 5 ppm mass accuracy, the peak comes out of the noise very clearly. That's what the high resolution exact mass really buys you. Right? So moving on. So what does 100,000 resolution really mean? We saw the results, but in the peak widths, what does it mean? So this is the peak width at 10,000 resolution. So you can see the butyl phthalate has a mass of 279,15909. Ethynyl estradiol 279,17434. It's just one white peak, cannot tell anything. If you run it at 30,000, this greenish peak, now you have resolved these two. This is ethynyl estradiol, this is phthalate. If you run it at 50,000 resolution, they are separated even better. And if you run it at 100,000, they are completely separated. And you can never make an error in quantitating ethynyl estradiol, even at very low levels like 500 ppb. So that's the power. Now, this is based on Orbitrap. So the one obvious question comes up is, okay, how quantitative is this? And as you can see, when you run this at 100,000 resolution, you get a perfect linear curve from 5 to 100 part per billion, or from 25 to 500 picograms on column injection. So it's a very linear quantitative device. Now, jumping to one example of forensic screening. So in this case, one of the forensic screening labs in Europe, in France, wanted to monitor and wanted us to show them how these 40 drugs, which are listed here, can be monitored and confirmed in serum sample. Now, this is basically a combination of benzodiazepines, opiates, kind of drugs, which are monitored quite a bit in forensic screening. Now, these color-coded things, they are either isobaric molecules or isomers. So, for example, you have, let's just take one example. So 325.1711, there must be a 325.1102. So these are isobaric when it comes to nominal mass instrument. Now we ran this from 0.4 micrograms per liter to 1.25 milligrams per liter. How was the sample prepared? Sample preparation procedure was told to us by this lab that we should follow their current methodology, which was basically liquid-liquid extraction. Take 1 ml of human serum, add 200 microliters of sodium bicarbonate, ether, vortex, separate the organic layer, dry, reconstitute, and inject. So nothing fancy, very simple. This slide basically shows what was the gradient used, what's the column, and this work was done using two different kinds of HPLC systems. One traditional HPLC, which used 150 by 2.1 millimeter column. The other UPLC, which used 1.9 micron UPLC beads, and slightly different LC methods. ESI source, mass range of 100 to 800, and we ran it at all different resolutions. Positive, negative switching, and then MS-NS after every MS scan. Okay? Now what this slide shows is that mass accuracy is not affected by the concentration or even lower resolution that we ran for these 40 drugs. So for example, if you take this levomethpromazine, you can see the mass accuracy is around 3.5 here at 1,000 milligrams per liter, and at 100 micrograms per liter, it's still around the same. So, and it is more or less same at all the resolutions. So the exactive, which is based on arbitrage, you could run it at any resolution and your mass accuracy is not going to be affected. Then after confirming that, this is how the final results look like. So we identified, just based on the exact mass, the retention time, and then additional confirmation using fragment ions that are generated in the HCD cell. So what you have on the x-axis is two data points, 100,000 resolution, 10,000 resolution, and then the the concentrations in serum. And on this side, we have the number of drugs that were confirmed. So as you can see, at 1.25 milligrams per liter at 100,000 resolution, we identified almost 38 drugs. At 10,000 resolution, which is here, we identify much less number of drugs. And then as you go down the concentration, the number of drugs that are confirmed drops. But up to 10 micrograms per liter, you still identify very large number of drugs, just based on the exact mass and the MS-MS confirmation. On this side, I'm just showing one example of the selectivity. So what you have is the entire LC run. This was run at 100,000 resolution, and this is an extracted ion chromatogram for this particular drug, zolpidem. And as you can see, you do not get any background, any other peaks in the spectra, even in this serum sample. It's very selective, very specific. Same thing for buprenorphine. This is a drug which is very commonly monitored nowadays and very important drug. And again, very clear peak at the expected detention time. Now, another way we can confirm the identity of a drug or any molecule is using isotope ratio matching. Now, how good is this for isotope ratio matching? So this is an example of resolution of 100,000. This drug, olanzapine, which has the sulfur in its elemental composition. If you run it at a resolution of 10,000, this is the C12, C13, then two C13s. And here, note this is how it looks like. You cannot tell whether this is really a pure C13 peak. But the moment you run this at 100,000 resolution, you can see this is actually two components, and they can be resolved at 100,000. And now, if you take the isotope ratio from here to this, they match very well. If you just take this, then the isotope ratios do not match the expected values very well. And that's again showing why high resolution is so important and so powerful. This is an example of now another drug, bromazepam, where these are the experimental relative intensities of the C13 or C12 to C13, and these are the theoretical ratios. And as you can see, just comparing this with this, they match pretty well within the error tolerance. Now this is an example of two drugs, meproptyline and amitriptyline. They have identical mass, identical in terms of nominal isobaric masses. They have slightly different structure. They look at different tension time, but pretty close. But they have different fragment ions. Now, if you look at just the LCMS extracted ion chromatogram, the first one is this M drug. The second one is the A drug. Now, it is possible that your HPLC is not very stable. The peaks can move, so you won't be able to confirm. But if you extract one of the fragment ions, which is unique to this particular drug, this perfectly matches with this M drug, and that's how you get additional confirmation. And this is also using accurate mass and high resolution. Now, another example from the same set of drugs, quinine and bisoprolol. They coelude. You cannot separate them most of the time. The C13 isotope of 1, which is the first one, 325.1911, matches with the C12, 326.2326. So, the C13 of one matches the other. They coelude. Now, how do we differentiate between these two? So, for example, here, if you have a sample which had both the drugs, then this will be a problem, because quinine, 325.1932, this is the C13 isotope, expanded zoom region here. And if you had bisoprolol, then that appears here. Now, if you run, this is at 100,000 resolution, very clearly separated. Here at 10,000 resolution, this, which is this, basically has a combined quinine plus bisoprolol. And if you get this, there is no way you can confirm whether you have bisoprolol in this particular sample, or is it only quinine. As we were asked to compare HPLC versus UPLC, we did those experiments, and what we found out was you gain roughly with UHPLC about 5x for 70% of the drug. So UPLC didn't help with all the 40 drugs, but it did help us with 70% of the drugs, increasing the intensity, getting better signals. The dynamic range for this analysis for these 40 drugs were 2 to 3 orders of magnitude, that is from 0.4 to 250 micrograms per liter. This is one example of the quantitation of one of the drugs, LSDs. Pretty linear. This slide, it's basically showing that with the UPLC, we can cut down the analysis time when we run exacted. So with UPLC, we were running around 20 minutes of runtime. The same samples, when ran with UPLC, we can cut it down to 8 minutes and still get very good quality results. So, as a summary of this identification and confirmation, HPLC versus UPLC, you can see the best results were really with UPLC at 100,000 resolution, which is here, right? This one. Now, how do we really identify these drugs? Whether do this all manually or you would do it with the software. And I think the obvious answer is you need a software that will go through this data, look at the MS masses, match the retention times, do the extracted ion chromatograms, extract the fragment ion masses, and then do the library matching. So we use the software for that purpose. It's called ToxID. It gives you different kinds of reports. This is just one example of a report where it is showing the drugs that are identified with the extracted ion chromatograms, the names of the drugs. So for example, the name of the drug is here, what was identified in one particular sample. It also gives you the formula that is extracted from the database. It gives you the exact, or it gives you the mass that was detected in the run. It tells you the mass error, comparing the experimental mass with the mass of this formula. And then it compares expected retention time with actual retention time. As you can see here, it gives you the information about the intensity, and then it tells you whether any of these drugs were found with any of the additives. So protonation, ammonia addict, sodium addict, and you can set this in the software. If you're looking for any salt addicts, then you can enter that information. And it tells you whether it was found with the salt addicts or not. So in conclusion, really, at least based on these 40 drugs that we identified and confirmed, you need a resolution of more than 50,000 to really extract out these drugs from the background and also from other isobaric drugs that are monitored in these forensic screening cases. You need better than 5 ppm mass accuracy. If you believe in isotope ratio matching to have additional confirmation for the drugs, then you definitely need to run an instrument at 100,000 resolution. You need additional MSMS if you wanted additional confirmation, and you do get that using Exactive. If you want the best of the performance, use UHPLC. That will cut down, not only increase your sensitivity, but also it will cut down your runtime. For these 40 drugs that we monitored in large number of samples, our LOQ or LOD was roughly around 2 micrograms per liter. For some it was lower, for others it was higher. And we confirmed that the Tox ID software that was developed for exact mass high resolution data works quite well. I think that was my last slide. So with that, I can take any questions that you may have. Okay, so since there are no questions, if there are any questions you want to ask after this presentation, we'll be here. Please feel free to talk to us.